So we are going to start with a quick discussion on why we aerate, some basic stuff and reminders. We are talking about aeration process because it is the single largest energy consuming process in wastewater treatment plants. As it is shown in the chart, up to 60% of energy consumption in wastewater treatment plant is due to aeration. So it is important to optimize energy consumption to save energy, which results in saving money for the plants, and also reduce GHG emissions, which result in saving environment. Also, the energy savings opportunities such as aeration optimization pay for themselves over the years. So what is the reason that we do aeration? Why we do it? Well, of course, we have carbon, ammonia, nitrogen as nutrients that are coming to the plant. So we do add oxygens to remove BOD. We do add oxygen to do the first step of nitrification or breakdown of ammonia into nitrate. We need also a little bit of oxygen for the second step of nitrification and converting nitrate into nitrate. We do add oxygen for mixing or maintaining suspension of materials, optimizing SVI, and if we need to get a tighter control to maximize low DO situations without going too low. So also well-operated systems increase the solid management capabilities. So these are the reasons that we do add oxygen to the plants. But how do we control aeration demand? Aeration demand depends on the characteristics of wastewater, such as organics and ammonia. Each of these steps need 50% energy. However, the organics, we can measure them as BOD or carbonaceous BOD and COD, but controlling demand, aeration demand based on these two parameters is not that practical because of the limitations of analytical methods. For example, BOD is measured over 5 days, so it means that it is not real time, and controlling aeration demand based on that is not going to be perfect. Also, we have due to influent conditions and conditions of the headworks, it is very difficult to maintain ammonia sensors, and we have due to the conditions of the headworks, it is sometimes it results in failed pieces. So these controlling aeration demand based on these two characters is not always practical. So what do we do instead? Instead of that, measurement of oxygen supply is used for controlling aeration demand, which has some positive and some negative aspects. On the positive side, measurement of oxygen supply is fast, it is simple, it is ideal process control due to its frequency and accuracy. But on the negative side here, it is not reliable since it does not measure oxygen demand. It is a lagging indicator, and therefore it does not have predictive value, which I'm going to talk about the last part in the next slide. Here, this top diagram is showing a conventional wastewater treatment plant, including a screen, primary clarifier, aeration basins with the DO sensors, and secondary clarifier. The bottom diagram is showing a PID control, which is a cascade control. The DO controller here, or the PI controller, calculates the airflow based on the difference between the DO set point and the measurements received from the DO sensors. The output from the PI controller is a set point for the airflow controller or the slave, which compares the airflow set point with the actual airflow, and it adjusts the basin or zone airflow valves accordingly. So therefore, due to the HRT lag between the load that's entering the plant and the DO sensors, there is no opportunity here to be proactive. For example, if a heavy load comes in, and that's why we are saying that it's a lagging sensor, and it does not have predictive values. So what else can be done to better control aeration control? Feed-forward control is another method, and here we are introducing SENTRY sensors for that purpose. But how does SENTRY sensor work? Using SENTRY as a BES system to support aeration control is another method. SENTRY is a bioelectrochemical system that's made up of anode and cathode. The probe itself is a small circuit that's designed to work using the biofilm that grows on these electrodes. As wastewater flows over the surface of the electrodes, the biofilm is growing on it, and the biofilm on the surface consumes the organic carbon traditionally measured as BOD, COD, or TATP. And as a result, we have a transfer of electrons between the two electrodes. And the free electrons that are released as the biofilm metabolizes the organic load are counted as electricity. So, in other words, we are measuring the ability of the biology in the process to treat the wastewater. Or in more simpler terms, it's like a heart rate monitor for the biology. If this chart here showing the live signal on the dashboard, if the line is going up, such as here, we are seeing the spike in the signal, it means that there is a large organic load coming to the plants, such as brewery waste. And if we are seeing a drop in the signal, such as here, it means that there are less carbon available due to a number of things, like dilution of wastewater due to heavy rain events or toxic chemicals. So Selena, I think it's time to pull up the polls. So based on the information that we have provided about SENTRY, which of the following options you think that is not a way that SENTRY can help with the aeration control? There are 4 options. If you could please take your time and answer the question.
Okay.
Thank you, Selena.
Yeah.
Just a second. Yeah, so the question was that which of the following is not a way that SENTRY cannot help with aeration control? The correct answer is option D. If the system is over aerating due to minimum mixing requirements, SENTRY cannot be used for aeration control.
Everyone got the answer right, Hamlin. That's pretty awesome.
Yep.
Awesome.
Here, this chart is showing SENTRY deployments by problem statement. So the blue verticals are the current focus verticals, and the orange one are the future verticals. Most of our problem statements are toxicity monitoring in mid-scale municipal plants, followed by monitoring toxicity in industrial plants, pulp and paper, AD industrial monitoring, and toxicity in larger scale municipal plants. We also have some projects which we are working into optimizing aeration, AD optimization, and also we are working with university and R&D groups and some other applications. So based on this information and the introduction provided, we believe that we can use SENTRY sensor as a BES system to support feed-forward aeration control. It can be placed after the primary clarifier to support, to improve feedback DO control. Here I'm going to talk about case study number 1. This is a wastewater treatment plant, which includes a screening, primary clarifier, 3-lane parallel activated sludge lanes, and followed by secondary clarifier. We have 2 sensors installed in this plant since 2019. We have 1 sensor installed after a splitting box and 1 sensor at the end of the ASB line. The plant is impacted by stormwater management, the plant performance. Small and large rain events affect first flush events. And to give a background, a small information about first flush, it is the initial surface runoff of a rainstorm, and during this phase, flow entering the system is high in pollutants. 66% of nitrogen effluent issues at this plant are linked to inadequate storm or rainwater management. Here I'm giving a little bit background information about the DO control at this plant. It is a feedback DO control system. The top graph is showing cumulative distribution of DO over time. The set point is 2 milligram per liter. 33% of the time, the control system is above 2 milligram per liter, and 10% of the time it is below 1 milligram per liter. So it means that potentially these 10% of the times are low aerated or prone to under aeration. Based on the analysis that we did, we estimate that 21% aeration savings are available, which is equal to $21,000 US per year. The bottom graph is showing overlay of DO profile with effluent ammonia concentration. Here, for example, it shows that extended periods of under aeration resulted in effluent ammonia spike, and ammonia breakthrough happened during this time. These 2 graphs are showing DO profile with SENTRY signal. The top graph shows that there are diurnal patterns in SENTRY signal. When SENTRY signal is coming down, it leads the elevated DO. We estimate that between 2 to 4 hours, there is HRT between the drop in SENTRY signal and the increased DO. The bottom graph is showing another time period between SENTRY signal and DO, and it shows the impact of rain event. Here, we are seeing, for example, SENTRY signal is above 700 between 26th and 28th of November and 27th of November, but there is a rainfall happening here, and we are seeing dilution of wastewater, and as a result, there is drop in SENTRY signal, and it goes to almost 300 on November 29. So, Selena, if you could pull up the second
Sure.
question. So the second question asks which options are true about first flush events. So the first option is occurrence of high concentration of pollutants within the initial stage, or occurrence of low concentration, and plot of pollutant mass against runoff volume can be used to identify existence of first flush. And the last option is both option A or C and C are correct. So please take your time and answer the question.
I'm going to be very happy if I get 2 out of 2 here, Manaz.
The pool will be ended in 10 seconds. Okay, I'll end the pool and share the result.
Thank you, Selena. So yeah, the correct answer is option D. We are seeing higher concentrations of pollutants during the initial stage of rain, and the plot of mass, pollutant mass against the volume can be used to identify first flush events. This plot is considered one of the fundamental concepts of defining or identifying the first flush phenomena in drainage system. So here I would like to pause a moment and explain about SENTRY signal multiplied by flow and why we think that's a useful parameter. Here the picture is showing SENTRY signal submerged in wastewater and flow passing by the sensor. And as flow passes by the electrodes, we are seeing carbon passing by the electrode as well. So based on the extensive analysis we did on the client data, we think that multiplying flow into SENTRY signal is providing a better insight into the loading. And therefore, in the next slides, SENTRY signal times flow have been used to show the results. This chart here is showing the cumulative distribution of SENTRY signal times flow over time. It is broken down into three set points. 33 and 66 percentile of the data were the set points. Lower than 33 percentile of the data was considered low load, or as you can see by the green box here. The medium load was considered between 33 and 66 percentile of the data, the white box. And high load was considered above 66 percentile of the data. In the next step, we calculated the average DO for each range. The average DO for low load was 5.2 milligrams per liter. So it suggests that over-aeration was happening when the low load was entering the plants. The medium load, the average DO was 3.5. And the high load, the average DO was 3 milligrams per liter. So it suggests that over-aeration was more possible when low load was coming to the plant. Here I'm going to show why we think that SENTRY signal or SENTRY signal times flow provides critical information about the characteristics of flow. The chart is showing SENTRY signal times flow, the blue line, flow, the red line, and SENTRY signal, the green line, between June 13 and 17. There are 2 time periods that I'm going to talk about. The first time period is June 15 to 16. The first flush event is happening here. We are seeing higher flow and a spike in SENTRY signal times flow. And the SENTRY signal, the green line, was also higher during this time period. It was around 350 before the first flush, and then it increased to 410. So we believe that this is the first flush event, and the flow was coming to the plant was highest strength. The second time period is June 16 to 17. It seems that another first flush event is happening here, but then we have dilution of flow. Flow is still high, but the SENTRY signal or SENTRY signal times flow is coming down. The SENTRY signal was 410, but it decreased to 150 afterwards. So this shows that dilution of wastewater is happening, and the SENTRY signal or SENTRY signal times flow is providing valuable information about the flow. Now the question is that how the plants responded during those 2 times that I talked about during in previous slide. So this is the same time period, June 16 to 17, time 1 and time 2. Time 1, we had the first flush event happening here, the SENTRY signal times flow. We are seeing the spike in that, but the airflow, which is the black line, is not fast enough to respond to this event here. As a result, we are seeing extended periods of under aeration. The DO is below 1 milligram per liter most of the time. And as a result, we are seeing a spike in effluent ammonia, which is shown by the green line here. And effluent ammonia is increasing to 12 milligrams per liter. June 16 to 17, the second first flush is happening. The airflow responds to that. But then afterwards, when the flow is no longer concentrated, the airflow is still remaining high, although it was not needed. So again, it was not fast enough to respond to the decrease in load. Therefore, it remained high, and as a result, we are seeing increase in the DO concentration, and the DO increased to 7 milligrams per liter. So this shows that SENTRY-based control system could have prevented these under aeration or over aeration events. Based on the analysis that we did on this client data set, we worked with Dr. Rob Smith from Black and Veatch to develop a guideline about using SENTRY sensor for feed-forward aeration control support. This control nicely integrates with DO feedback system, and this picture shows the threshold analysis steps. So the threshold analysis is what I explained in the previous slide. For example, for this client data set, we use 33 and 66 percentile to estimate the low and high load range. It's based on the same concept. So here, the first step is to acquire the wastewater flow from the flow meter. The second step, acquire sensor SENTRY signal from the SENTRY sensor, which is placed after the primary clarifier. Multiply them together and evaluate the load to calculate the high or low threshold based on the set points showed in previous examples. If it is a high threshold, we need to establish QR max, and if it is low threshold, establish QR min. And then the next step is to get the DO from the DO sensors in each zone and evaluate airflow set point based on that. So, and then the error is calculated between the actual airflow and airflow set points, and the airflow can be adjusted based on these steps. After developing this guideline, we tested the logic in on data, and we developed the logic in Excel, and in the next slide, I'm going to show how the logic was working in Excel. So here, top graph is showing the actual DO profile with SENTRY signal times flow from November 7 to November 9. We are seeing periods of over aeration, such as here or November 9, when DO was almost 6 milligrams per liter. So the logic examines the SENTRY signal times flow. For example, on November 9, the SENTRY signal times flow, based on the conditions that we defined, it is saying that, okay, this is a low load coming to the plant, but the DO was above 2 milligrams per liter most of the times. So it examines the load, it examines the DO, and concludes that the action that needs to be taken here is to reduce the airflow. Negative 1.5 is reduce air because the load is low and the DO is above the set points. So we are still working on this guideline, and we are trying to improve it, but it seems that it is working in Excel. This is the second case. We have another aeration project, which is currently in progress in Atlantic Canada. We have installed 8 SENTRY sensors in this plant. One of them after the primary clarifier, 6 sensors in aeration cells, and 1 sensor at the effluent. We are currently collecting the data. And the goal is to leverage SENTRY signal DO airflow to profile existing aeration and delivery efficiency and define potential economic and environmental opportunities. We are also working with DHI and APG NOROS for aeration optimization assessments. Here it is showing the actual data collected from this plant. The top graph is showing profile of SENTRY signal times flow with the DO. Same as on case 1, we are seeing diurnal patterns in the signal. And when we are seeing a decrease in SENTRY signal times flow, it leads increase in the DO. This plant is similar to case 1, a feedback DO system, and the set point is 2.5. The bottom chart is showing time percentage of DO. 39% of the time it is under 1 milligram per liter. 30% of the time it is over 2.75 milligram per liter. So we estimate the goal is to reduce the under aeration times and reduce 39 the over aeration times as well. The next step for this project is to try suggested aeration control logics on local plant SCADA with no control of actual plant. And depending on the success of this step, in third phase, we are going to implement the logic on 1 reactor or 1 train and monitor the results for a set time period. To conclude, SENTRY can be used as a feed-forward system to support aeration control, and comparing to a feedback DO system, we are improving. We believe that we can improve the feedback. We just try to peak shave the DO feedback since they cannot act fast enough, and we do continue to work on this and improve it. We estimate that using SENTRY for feed-forward aeration support, we are able to help plants to save up to 20% in energy savings. We are eager to work with partners, with aeration groups, optimization groups. So if you are interested, please contact us. And we have another webinar on December 6th, which my colleague, Dr. Colin Ragesh, is going to talk about the smart aeration and BNR using SENTRY signal, using machine learning and AI. So thank you. And we are going to take the questions.
Thanks, Manaz.
Thank you.
That was awesome.
Thanks.
I'm not sure who we have external here. We have Bruce and Roland. Okay, cool. Jack, Colin, Cash, anybody with questions?
And Bruce did write one in the chat. He just said, looks like they have pretty bad DO control in the first place. They need to fix that to understand the benefits that SENTRY can give. And I'll start on that, and I can maybe throw it over to you as well, Manaz. But yeah, I definitely think it's a great point. I think it's actually it's a helpful case for us because we can really see the results of the poor aeration or the way that they don't handle the load well. So it does give us kind of a nice positive reaffirmation without enough intervention from their aeration system. I'd also say that they are like kind of relatively terrified of getting these first flush events. So they've definitely overtuned the air, you can kind of see it in the data that they've overtuned the aeration to excessively over aerate because they're not kind of able to determine when these first flushes coming in if they're higher load organic loading. So that's definitely the case with this system. Manaz, do you want to talk at all about some of the other plants that we've looked at in relation to this?
Yeah, we have looked into 10 plus aeration data sets from recent clients, and we have seen that there are a lot of opportunities to optimize the aeration systems, and we are eager working to them. We are in communication with this plan, so we believe that there is a lot of opportunities to use SENTRY sensor to support aeration controls.